to Covestro's 4th edition of Stay at Home STEM. We hope that this video finds you well and healthy during the coronavirus pandemic. My name is Matt Pulio, and I'm a technical service representative in Covestro's Polyurethanes Flexible Foams group. For today's experiments, we're going to be doing a few lessons involving cans of Coke, as well as teaching you how to make a sweet treat for you and your family. So for our first experiment, we're going to learn how carbon dioxide plays a very important part in cans of Coke. So let's head outside to do just that. Boy, it's really a nice day today. In fact, it's such a nice day, I think I'm going to play a trick on one of my roommates. What I'm going to do is I'm going to shake up these 2 cans of pop we got here. Make sure they're both nice and shook up. What I'm going to do is I'm going to have no issues opening my can of pop. But when my roommate comes out, I'm going to have a little bit of fun with it. So you can see, I'm currently flicking my can. And that's going to be the secret to this experiment. Hey JT, why don't you come out here?
Alright, what's up?
Hey, I brought you a Coke. Why don't you sit out here? It's a nice day.
Oh, thanks. Yeah, that was pretty nice.
Yeah, enjoy, man.
Whoa, 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 whoa.
Drink it.
Getting busy there.
A little bit. I mean, I shook both of them. You can check the videos, and I'm not having any issues with mine. You're actually lucky I didn't shake that more. It could have been a lot worse for you.
Oh, man.
Well, you see, I had no issues opening mine. Now let's go back inside and see why. So how did our experiment work? Well, to learn the secret of the fizzing can, we break down exactly how carbon dioxide is dissolved in the pop. So as you can see, carbon dioxide, which is made from carbonic acid, is found inside of the pop solution that's inside the can. So whenever we shake the can, what we do is we take this carbon dioxide gas and we spread it to the outside edges of the can. So the gas bubbles try to make their way around the edges and especially into the air that's right at the top of the can. That means that when we open the can, well, the only places that gas has to go is out through the top. So it makes a mad rush and comes out in a huge spew. Now, in what you saw today, I didn't shake the can too much because I didn't want to have to be flicking my can for very long. Because the longer you flick the can, the more carbon dioxide bubbles you can control. So now, let's take a look at my can. Again, started off with carbon dioxide dissolved in the pop solution, shook it up to get it to the outside. But now what I did was I started flicking the sides of the can. And what that was doing is it was actually forcing the carbon dioxide bubbles back into the solution. So after about a minute of flicking, I was able to get the bubbles of my can back in the solution, so when I opened it, I didn't have the mad rush to the top like JT did. Now, this is very interesting, but it also applies in many other ways in life. So to see how CO2 solutions can be used at work, we're going to take a look at how it is used in making polyurethane foam. So what I do on a daily basis. Well, to make polyurethane foam, it involves a mixture of 3 components: polyol, isocyanate, and water. When we mix these 3 components together, we kickstart the reactions that will make memory foam or other foams that you might have seen before, like in your car seats, car cushions, couch cushions, and any type of bedding application. So we mix these 3 components together, and well, what do we get from there? There are 2 reactions that occur when making polyurethane foam. First is the polyol and the isocyanate react to create polyurethane. The water and the isocyanate react to create carbon dioxide. So what happens is the carbon dioxide gets dissolved in this solution, as shown here. So if you consider these squiggly lines as the polyurethane, the CO2 represent these bubbles in here. Now, just like a can of pop, this is suspended in the solution, but this carbon dioxide will try to expand. This is what creates the foam rising. So, for those of you who haven't seen an actual piece of foam rising before, imagine it like a loaf of bread. Whenever you're baking bread, you have 3 ingredients: flour, sugar, and yeast. And when you mix these together, you also create carbon dioxide gas, just like you would if you were making polyurethane foam. That carbon dioxide gas expansion is what causes a loaf of bread to rise. So, when you're thinking about making polyurethane foam, just think about a loaf of bread rising. So once the CO2 rises, you now have a nice bun of memory foam. And so very appropriately, we also call foam a bun because, again, it is like a loaf of bread. So now, in both of these cases, it's very important to have CO2 dissolved in our solution, because without carbon dioxide, All three of these applications, a can of pop, a loaf of bread, and polyurethane foam, would all create a big mess if we didn't have carbon dioxide dissolved correctly in each of these solutions. So for our second experiment, we're going to see if cans of Coke will either sink or float. So first, I'm going to take a can of Coke Zero and Cherry Coke, completely empty, and toss them in the water. I like that noise, by the way. And no surprise there, they're going to float. So now let's take a can of regular Coke, completely full, and when we put it in the water, it sinks to the bottom, like a rock. Now let's take a can of Coke Zero. And when we put the can of Coke Zero in the water, it pops back up and wants to float just like the empty cans. Now, the important thing about these two cans of Coke is that they are in fact different. One is Coke Zero with zero sugar, one's regular Coke that has sugar in it. So now let's break down how this impacts density and how this tells us which one is going to sink or float. So now let's uncover the mystery of why the cans either sink or float. Now it's important to remember that it's all about density. So density is defined as the mass of an object divided by the volume or the amount of space that object takes up. Now the density of water is 1 gram per milliliter, meaning 1 milliliter of water weighs exactly 1 gram. Now to see if something will sink or float, you must look at the density of that other object. If the object has a density greater than 1 gram per milliliter, it will sink. But if it has a density less than 1 gram per milliliter, it will float. Now, let's start by calculating the volume of a can of Coke. The volume of a can of Coke is defined as pi times the diameter squared, that's the distance across the top, times the height of a can of Coke, all divided by 4. So I took these measurements earlier and found the diameter to be 6.3 centimeters and the height to be 12.1 centimeters. So when I plug that into our formula, I got a volume of 377 cubic centimeters. Now 1 cubic centimeter is equal to 1 milliliter, so we can say that the volume of a can of Coke is 377 milliliters. Now this will kind of act as our threshold. If an object has a mass greater than 377 grams, it will have a density greater than 1. But if it has a mass less than 377 grams, it will have a density of less than 1. So now let's look at the masses of our cans of Coke. Now the only way to find mass is to actually measure the can of Cokes on a scale. So I did this earlier, but let's just put these on here to check everything out. So Coke Zero, 369 grams, that checks out. And the regular Coke, 382 grams. I got 383 earlier, so that checks out as well. So now when we look at the density, we see the Coca-Cola can has a density of 1.016, which is greater than 1. That's why the can of Coca-Cola sunk to the bottom. However, the can of Coke Zero had a mass less than 377 grams, it was 369 grams, and that gave us a density of 0.979, which was less than 1. And that explains why that can of Coke actually floated. So, what actually causes this? As we said, Coke Zero doesn't have any sugar in it. So it actually has some artificial sweeteners like aspartame that actually weigh less than the sugar that's in the regular can of Coca-Cola. You need less sweetener in here in order to give it the same taste. So that's what causes these mass differences here. Now, to look at how much this actually is, we're going to weigh out the 40 grams of Coca-Cola or 40 grams of sugar that are in a can of Coca-Cola. So we're going to tear our balance, getting 0 grams. And as we add sugar, we'll see the mass increasing. And that gets us to about the 40 grams of sugar that are in this can of Coke. So all this sugar is what's weighing down this can of Coke and is causing it to sink to the bottom. But this sugar is not present in the Coke Zero. So it's a little bit lighter, and it gives it that ability to be lower than that 377 milliliter threshold that we need for an object to sink or float. Now for our last experiment, we're gonna make homemade ice cream. So, since I feel bad for spraying JT with Coke earlier, JT,
Yeah, Matt.
So, I'm very sorry for spraying you with Coke. So, how about you make some ice cream with me? Would that be better?
Yeah,
All right, excellent. So, here are the ingredients that you're gonna need to make your own ice cream. I'm gonna hold it up here. Feel free to pause the video or take a screenshot. I'll leave the recipe down there. So, let's start off by making our ice solution. So, we're gonna take advantage of a phenomenon called freezing point depression today. Now, freezing point depression occurs whenever you add salt to a solution. It'll actually lower the freezing point of that solution and make it even colder. Now, whenever salt is dissolved in a solution, it pulls energy out of that solution, leaving it with a lower temperature. Now, that's gonna help us to cool our ice cream a little bit quicker today. So to do that, we're gonna take our bag of ice and we're gonna add 1/3 cup of the kosher salt to it. I'm getting salt all over my countertop. That's okay. Now go ahead and give that a good shake. So you might notice that the bag is feeling a little bit colder because, as I said, the salt being dissolved is actually pulling energy out of the ice. So let's hang on to those for now and let's get our ice cream mixture ready to go. We're now going to mix the other components. So a cup of 50/50. There you go, sir. Mm-hmm. So we'll add a cup of 50/50 to a small bag. We'll then add 2 tablespoons of granulated sugar. And a 1/2 teaspoon of vanilla extract. Here's my extract. Oh, it's a new bottle. To give it a little bit of flavor. Spilled a little bit extra there, but a little flavor never hurt anybody. So go ahead and seal that up. So make sure it's nice and sealed. And then go ahead and put that in your ice bag solution. Now, JT, go ahead and shake that for about 10 minutes now. And since it's gonna be really cold, you're gonna wanna use a pair of gloves. Oven mitts work, or even a pair of winter gloves can help as well, just to make sure that your fingers don't freeze. That's obviously bad. Thank you, Mr. Cameraman. And a little bit more extract. How you doing over there?
Doing well so far.
All right, got about 10 more minutes to go. So now, during this time, talk to your parents, talk to your siblings, maybe even call your grandparents on the phone, watch a TV show, listen to your favorite songs. There's a lot of things that you can do. So since JT has our oven mitts, I'm gonna take my Pittsburgh Penguins pot holders here, let's go Pens, and start shaking my bag as well. Now this is gonna take some time, and we don't want you to wait the entire time, so we're gonna fast forward to when this is done. Kill it. Okay, no, it's really not that bad. So, now that the time has passed, we've got our mixture nice and thick. We're gonna add our ice cream to our bowls. There we go. Come on. I ended up double bagging mine just to give it a little extra safety.
Oh yeah, that came out good.
Yeah, yours came out really good. So we'll take a spoon and get the rest out of mine. Or just eat it. Mm. And now, top it off with your favorite toppings. I can't get this open because my fingers are wet. There we go. For me, that topping is M&Ms. Would you like some M&Ms too?
I love some M&Ms.
Perfect for a warm summer's day. That's it. So while I'm enjoying my ice cream, I want to wrap up today's video and thank you for joining us today. Now I hope you learned a lot about how CO2 is important when dissolved in solutions, how to calculate density, and also how to make a sweet treat for your entire family. Now parents, I hope that you've got something out of this as well. Whenever you're sitting by the pool and your kids begin to annoy you, just take a can of Coke, toss it in the pool, and make them dive after it. However, be sure it's a can of regular Coke and not Diet Coke or Coke Zero. Thank you again for joining for our 4th edition of Stay at Home STEM. Take care.